All right, so yesterday or not yesterday, Tuesday, we talked about identifying unique sets of protons and carbons in various molecules. We said you have to watch out for symmetry elements, things like that. And then we said that the relative size of the peaks is correlated to the number of protons that account for that signal, right? So it's just a ratio. In this top example, we said it could be 300 to 200 to 100. The important thing is that it's a 3 to 2 to 1 ratio for those peak sizes. So it's a relative ratio. Today, what we're going to look at is kind of related to this. In this example, we predicted that we had two different peaks, one for the red protons, one for those blue protons, and we said that it would be roughly a 9 to 1 ratio. But if you notice, those peaks that I'm showing you right now are just nice, clean peaks. The truth gets a lot more complicated than this. All right, so let's take a look at signal shape. All right, this gets into some physicsy stuff, but I'm going to boil it down to OChem level. And it has to do with the spin states of nuclei. So nuclei can be spin up or spin down. You might remember that from Gen Chem. Can be spun up? Spin up? I'm not referring to it as like a verb. I'm just saying it's a noun, spin up, or I think it's spin up. Oh my goodness. And they can have, shh. You're ruining the story. And they can have spin-spin coupling. And I'll describe what coupling is. Oop. With neighboring nuclei. That essentially means that one nuclei, if it's close to another nuclei of the right type, can actually feel that nuclei in space. It's kind of cool. All right, so let's take a look at this, and I'll kind of explain it in really loose terms. So let's look at an example. And I'm going to call this H sub B in blue. Affect our proton of interest, which I'm just going to call HA. Right? So we'll take a look at this with a handful of different examples. In the first example, I'm just going to kind of make up a molecule, and I'm not going to show all of the various attachment points. We're just going to make it kind of simple. We've got two protons that are adjacent to each other like this. We're going to say that HA is on the left and HB is on the right. So HA as a proton in this situation can actually feel HB in space through spin-spin coupling. So let's take a look at possible HB spin states. All right, we know HB as a neighboring proton can either be spin up or it could be spin down. Do you think one's more likely than the other? Nope, 50-50 ratio. So this is always going to be a 1-to-1 ratio. So if we think about the peak for HA, HA is going to actually reflect that 1-to-1 ratio of the possible spin states for HB. So what the peak will look like is almost like a pair of fangs, like this. This is called a doublet. Oftentimes just abbreviated as a D. So on the NMR spectrum, when we're looking for the peak for HA, if it has one neighboring HB, it'll actually be a signal that's split into two peaks, a doublet in this case. But it'll be a pretty tight pair of fangs in there. So it's not going to be spread apart very far in the spectrum. They're going to be two adjacent peaks that are really close to one another. And I'll show you examples so you know what to look for. All right, let's do a harder one though. I'm going to color code all of this. So again, we're going to look at HA, but this time we're going to assume that it has two HB neighbors. So we've got a few different possibilities. One is that both of those HBs are spin up. Does that make sense? One could be that one is spin up and the other spin down. However, this can occur statistically two different ways, right? So maybe the top HB is spin up and the bottom HB is spin down, or maybe the top HB is spin down and the bottom HB is spin up. Statistically, this can happen two different ways, or potentially they could be both spin down. So if we think about the statistical probability of the HB spin states, it's going to be a 1 to 2 to 1 probability ratio, right? So if we think about the peak here that we'll observe for HA, it's actually going to look almost like our stack of blocks, like a little trident like that. This is going to be a triplet abbreviated as T. Does that make sense? Yep.
So if they're the spin up and spin down, those two will give the exact same like effect on HA?
Yeah, so your question I think is about these, saying, do they have the same effect? Absolutely. Okay. HA can't really tell the difference between one being spin up and the other spin down versus the other one being opposite of that, so to speak. Okay, so let's go one further. Let's say we have 3 neighboring protons to HA that we're looking at. If we think about the possible spin states for HB, all 3 could be spin up. That's possible. Or maybe we've got the first 2 spin up, third spin down. Or maybe we've got the first spin up, second spin down, third one spin up. Or maybe it's spin down, up, up. The net effect of all of these, in this column at least, are 2 spin ups, 1 spin down, right? Make sense? So the same net effect. Or maybe we've got 2 spin downs, 1 spin up. Or maybe we've got spin down, up, down. Or maybe we've got up, down, down. In all 3 of these combinations, the net effect is 2 spin down, 1 spin up, right? And then the last one, what do you think that's going to be? Down, down, down. All right, so what do you think the ratio is going to be for this peak? 1 to 3 to 3 to 1. All right, so if we try to predict the signal shape for HA in this specific example, HA is going to have a side peak that's pretty small because it's going to be 1/3 as big as these middle peaks. But the middle peaks will actually be the same size. And then the last peak will come off the side like that. Does that make sense? So if we look at this peak, it's roughly 3 times as big as the little side satellites coming off of there. All right, this is called a quartet, often just abbreviated as a Q. Yep.
So what happens if you have another carbon with 3 more protons coming out of it?
Yeah, so you're asking what if we have more neighboring protons? All right, so let's take a look at the trend here. What do you think would happen if we had 4 neighboring HBs? What would the peak be? What would the peak be called if we had 4 neighboring HBs? A pentet, right? The peak would be split into 5 peaks, right? So that leads us to the next trick that I'll show you. That's called the n+1 rule. So let's say we've got 4 HBs. HA we said would be what? Yep, a pentet. What if we have 5 HBs? A sextet? What about 7? An octet? You can keep on going up and you can actually predict the signal shape based on the numbering of neighboring protons. So just add 1 onto that. All right? There's a couple of other rules that are also very important to remember whenever you're doing NMR, but after you do it for a while, you just intuitively use them without thinking about them. HA, the proton that we're looking at the shape of, can only feel protons that are 2 or 3 bonds away. All right, so let's go back up and look at this in the context of the examples that we were looking at, right? So if we go back up just 1 second, and we look at HA in this example here, what I mean by number of bonds away is we count, right? We go 1, 2, 3. Because HB is 3 bonds away, we can feel that. If it were 4 bonds away, we wouldn't feel those protons, and HA wouldn't be split by those sets of protons. You can only be split by protons that are 2 or 3 bonds away. Yep.
So does that mean the highest would be 9 then?
Not necessarily. There's a bunch of weird situations. We'll see more and more examples. I'm just giving us the brief intro. Yep.
Does that only count for single bonds? Does like double bonds because there's 2?
You can go through double bonds. Absolutely. Yeah. Good question. Yep.
Why not 4? Like, what would limit it just to 2?
So we'll go back and we'll talk about this. So the closest you can be to an adjacent proton that's different is 2 bonds away, right? It can't be 1 bond away. Otherwise, you're looking at hydrogen.
Yeah, I was looking at like interfere with it, feeling that 3rd bond.
Yep. So if you're looking at splitting from a neighboring proton that's 2 bonds away, those peaks tend to be split wider than if they're 3 bonds away. Those peaks tend to be split much more narrow. Yeah. All right. The next thing that's also important is when we're looking at HA, it cannot feel or be split by other HAs. That is to say, equivalent protons don't split one another. So let's even write that down. All right, and then last but not least, this is a general rule of thumb. It's true for most organic molecules. HA cannot feel protons if you must go through a non-carbon atom. To find a neighbor. So what I mean by that is if you're doing that 2 or 3 bond search to find a neighbor and there's an oxygen that you have to travel through to find that neighbor, you can't do that. We're really not going to get into the whys behind that. That has a lot to do with pretty advanced physics that, to be perfectly honest, I'm not even comfortable explaining. All right, so let's take a look at this in an example. Oops. And in this example, we're going to be looking at C2H6O. And we can even draw out this molecule. We've done this a couple times in class already. but we'll try to make sense of an actual NMR spectrum. So we've got ethanol over here. We already said on Tuesday that these HAs are equivalent to one another because that methyl group is basically spinning around like a little propeller blade. All right, and then HB over here, these are equivalent to one another. And then HC over here is unique and all by itself, right? So we would expect 3 different signals. And if we were to go through and make a little chart, we could do kind of what we did the other day. We could do HX in one column. We could do integration in the other column. And then we could call this the multiplicity or the splitting pattern that we expect. And we know that we've got HA, which is different from HB, which is different from HC. We know that the protons making up HA are a relative area of 3 to 2 to 1, right? All right, now if we look at HA, how many neighboring protons are there to HA that are 2 or 3 bonds away? 2, right? So the HBs are 3 bonds away to one of the given HA atoms, right? So normally when I do this, I just focus in on one specific HA atom, or proton in this case, and then I ask myself, for this specific proton in HA, how many 3 bond neighbors does it have? Well, we have 2. What will the multiplicity be? It'll be 3, or a triplet. Right? Because we have 2 3 bond neighbors to HA, it's going to be the n+1 rule, means it'll be split into a peak of 3. All right, HB, if we think about it, let's again focus in on just one of these HB atoms. We can kind of ignore the other one because it's equivalent. How many 3 bond neighbors are there to HB? Why don't we count HC? We have to go through an oxygen, so we can't count HC because we're going through a non-carbon atom. So HB in this case has 3 3 bond neighbors, which means it'll be split into what? A quartet. All right, and then last but not least, we've got HC. HC, how many 3 bond neighbors does it have? 0. We can't go through that oxygen atom. So in this case, 0 plus 1 is 1. It'll be a singlet. All right, so now this NMR spectrum is going to make a heck of a lot more sense. If we look at this peak right here, what do you think that belongs to? HB, okay? So we can immediately go through and we can say, we predict that this peak belongs to HB because it's split into a quartet, all right? And then this peak right here has to be what? HC, because it's a singlet. The other thing you might notice is HC, in this case, is much, much, much smaller than HB. If we were to use a computer and find the size of the peak, it would be 1/2 the size of the entire quartet for HB. And then last but not least, we know that this one must be HA because it's the only triplet. And in this case, it's 3 times as big as HC. And like I said, the area is going to be the area underneath all 3 of those prongs. So the computer will actually integrate the entire area underneath all of the peaks that are being split. Make sense? All right, so let's do a harder one. Okay, so for this challenge problem, let's do it this way. We'll do a bromine there. What I want you to do is to make a predictive table, kind of like we did in that last example, where we determine the number of unique protons, their relative integration, and their multiplicity, meaning what will the signal be split as? So before we get going, how many unique protons are there? 4? I agree. So let's go through and label them. I'm going to label these all as HAs. These are going to be equivalent to those HAs, and why is that? Symmetry. We can cut this molecule vertically down the middle, The left half is the same as the right half. Then we've got HB over here, got HC down here, got HD down here. So we've got 4 different protons, so hopefully that can get you started. All right, give me a thumbs up if you think you got this one. Thumbs up if you think you got it. All right, so let's take a look at HA. There's 6 total protons making up the signal for HA, so I'll just put in 6 here. There's 1 for HB, there's 2 for HC, and there's 2 for HD. Not too bad. All right, now if we focus in on just one of these HA protons, how many 3-bond neighbors does it have? 1, right? It only has 1 HB proton that's a 3-bond neighbor, so what will the multiplicity be for HA? A doublet. It's going to be a pretty big doublet because there's 6 protons making up that signal, right? So it's going to be 6 times as large as the signal for HB. All right, so now let's jump to HB and ask ourselves, how many 3-bond neighbors does HB have? 6. So what will its multiplicity be? A septet. That just means a signal shape of 7, right? All right, if we think about HC, how many 3-bond neighbors does it have? And remember, this is the thing where students get confused, is just focus on one of them. Don't focus on both of them, just one. A doublet. All right, and then last but not least, if we think about HD, what will that be? HD will also be a doublet. All right, so what I want you to do for the problem of the day is I asked you to draw the spectrum. Don't do that. We haven't gotten that far yet. Just include a table like this for that unknown molecule. Yeah, that's a good question. So HC, if we look at it, we're just focusing on one of the HC protons. And if we look at HC and we try to find a 3-bond neighbor, we go 1, 2, 3. Can't go 1, 2, 3, 4, right? So we can only see 3-bond neighbors. We can't go out to HB because that's actually 4 bonds away. Great question, though. All right, so that's where we'll stop today. Next week when we come back, we'll look more at the intensity of splitting. And then we'll do a lot of practice problems next week, including in lab. Next week's lab is a bit different, so make sure that you read through the pre-lab. You don't have to prep your notebook like normal. Just make sure you come into lab knowing what you're supposed to be doing when you get into lab.